All right, in this module, we are going to talk about point groups and we're going to talk about crystal systems. Sorry. And this is a continuation of what we've talked about with all these different symmetry operations. So, a point group, and these are 10 point groups. A point group is the different symmetry operations acting on a point, and they're grouped together. So essentially, the first one, the least amount of symmetry, is if we have an arbitrary point, and it's 1. So this is the self identity. So we rotate it 360, right, in the same position. So this is basically no symmetry. But we can basically imagine a set of 10 of these different, and so you'll notice that they're some of these symmetry operations that we talked about, and also different combinations. So the 2 is the twofold inversion, the twofold rotation. So that's what the 2 is here. There's also the mirror. So this is M for the mirror plane. So there's a mirror plane going in this direction. And so that causes the point to change. There's also a twofold rotational axis here, and then 2 mirror planes, and so on and so on. So there's different combinations of those different symmetry operations, and this is in 2 dimensions what we define as the point group. And so there's basically 10 of these. So the continuation of that is if we go to 3 dimensions, then there ends up being 32 point groups that give us the different symmetry operators in 3D. So there's 32 point groups in 3 dimensions. So instead of trying to draw them all out, I've just kind of put a system here. And so this is kind of a map showing you those 32 point groups and which are more symmetric. So up here at the top is the most symmetric point groups, and then down here at the bottom, 1 is always going to be the least symmetric, and then anywhere in between you can kind of see the relative symmetries of these various point groups in 3 dimensions. So basically, this is comparable to trying to describe the periodicity of a lattice with translations, right? So instead of doing translations, we're defining the symmetry in these different point groups or combinations of those 4 macroscopic symmetry operators that we talked about. So rotations, reflections or mirrors, inversions, and roto-inversions, right? So we can define all of those and combinations of them in these 32 different 3-dimensional point groups. All right. So now that we talked about these symmetry operations and then putting these together in point groups, I want to take a step back and look at crystal systems. So what a crystal system is it's a combination, a unique combination of the lattice parameters that we talked about, those vectors, A, B, and C, and then the angles. So the different systems are basically defining the different shapes of this point lattice. So cubic has, again, the vectors would be A, B, and C. The lengths of those vectors are all the same, and then the angles between each of those vectors is 90. And so we get a cubic shape like you see over here. Tetragonal is the case where we have A and B, the lengths are the same, but the C vector is longer or shorter. It's not the same, but all the angles are still 90. And so that's tetragonal over here. Orthorhombic has a different combination of lengths and angles. So we talk about these lengths and angles as the lattice parameters. And so for this, all the lengths are different, but the angles are all still 90. Rhombohedral, all the lengths are the same, but one of the angles is different. Hexagonal, you might be familiar with. The 2 of the lengths are the same, the C is not, and then 2 of the angles are the same, but the third is specifically 120. And then monoclinic has less equal, so essentially none of these are equal, and then one of the angles is non-90, and then the last one, nothing's the same. So A, B, and C are all unique, and the angles are all unique as well, and that's triclinic. So these are the 7 systems. So the 7 different combinations of lengths and angles that define different shapes that we're going to build lattice points on. So that's what we mean by crystal systems. We have 7 unique ones with different combinations of lattice parameters and angles. But again, we haven't defined anything in terms of the points yet. So if we now put points to these shapes, we get point lattices. And there's a scientist, what we'd call a crystallographer, that showed that if we put points on these different systems, there's only 14 unique possible point lattices that are available. So only 14 of those point lattices. Because that crystallographer's name was Bravais, then we call these the Bravais lattices. So this is what you see in this column here. So if you kind of count all of these and they're shown over here, there's 14 of these Bravais lattices. So we've taken the shape, cubic, tetragonal, orthorhombic, so forth, and we've added points onto them in different arrangements, but there is only 14 unique. So what that means is that if I can think of a different one, right? So let's say I can think of tetragonal, but it has an arrangement of what we would call face-centered. So it would be tetragonal like this shape, but it would have all the points that you associate up here. Well, what Bravais did is he proved that can be described in a different way to be one of these other point lattices. So this basically describes all the possible point lattices that there are. And so that's why we call these the 14 Bravais lattices. So we've identified different crystal systems, the 7 that we talked about. We've talked about the 14 Bravais lattices. So now I want to mention and connect it back to the symmetry operations that we just dealt with. So if we think about for each system, there's a minimum symmetry operation. There are a minimum number of symmetry operations for each of these systems. So if I start with cubic has a minimum of 4 of these 3-fold rotation axes. So this is what you saw in the dice activity earlier, right? There was 3-fold rotational axes, and there ends up being 4 of them. So that's the minimum number of symmetry operations for cubic. But it often has a lot more. Tetragonal, on the other hand, only has 1 4-fold rotation axis. So that's the minimum number that we have. So again, it can often have more, but it at least has to have 1 4-fold rotational axis. Orthorhombic, make sure I got the spelling right there. Orthorhombic has 3 perpendicular 2-fold rotation axes. So it has at least 3 perpendicular 2-fold rotation axes. Hexagonal has a minimum of 1 6-fold rotation axis. And then way down at the bottom, the least symmetric, triclinic, it has no minimum symmetry. So basically that would be that 1, right? The identity matrix, or sorry, the identity operator. So it doesn't have a minimum because it's the least symmetric. It's on the lowest end of that form that you saw. All right, so those are the minimum symmetry operations that we have. So what I want you to do with the quiz question around this is that I want you to look at the slide that has all the 3D point groups, and it shows it in ranking of symmetry. And I want you to think about those different symmetry those 32 point groups, and I want you to think about those point groups and see which ones most closely tie with the given systems. So which one looks most like cubic? Which one of those point groups looks most like cubic? Thinking about the symmetry that I've talked about here. Which one looks like tetragonal? And which one looks like hexagonal? So again, which one looks the closest to what you associate with the minimum symmetry? So see if you can do that, and then we'll come back and discuss this. All right, so let's take a look at the quiz question I asked in terms of which of these point groups that you see would look similar to cubic, tetragonal, and hexagonal. And so what I want you to do with this exercise is think about that minimum symmetry operation, right? So for cubic, we talked about 4 threefold rotation axes. So the threefold is represented by the number 3, right? So if I'm scanning around here, I see 3 over here, I also see 3 over here, and so all of these here have a threefold rotational axis, right? All of these have 3s in them. So we're not really, so right now, you don't necessarily know how to read this M3 bar M, but you see the 3, which signifies a threefold roto inversion. You see 3s here, and all of those are rotational axes. And we also know that cubic is very symmetric, right? So that would tell me that one of these operators is cubic. And in fact, all of these are different cubic, are all in the cubic system. So different, and this is the most symmetric of all the cubic and all of the point groups, right? So we can kind of associate these with cubic, right? So, just any one of these would work. Tetragonal, I mentioned that there has to at least be a 4-fold rotational axis, right? That's the minimum. And so you see this cluster over here that has 4s, right? 4, and then you see some M's, 4 2s, all this, but there's a lot of 4s over here, right? So that's the minimum operation for tetragonal, and this is, so these, any of these you could put down as relating to tetragonal. So that's kind of, I'm just looking for you to associate that minimum symmetry operators to what it appears like in these different point groups. And lastly, hexagonal, we know that we have at least one 6-fold rotational axis. And again, if you kind of scan all of these and look for 6s, you see a lot of 6s over here, right? And so these are tied to hexagonal system because we have the 6-fold symmetry, and this is the most symmetric of those various hexagonal point groups. So we can associate any kind of one of these with the hexagonal system. So I just want you to kind of associate, because we're not going to talk as much about individually what these mean, but I want you to have a basic idea that if you see the 3 kind of associated in any of these, that this is probably a cubic system, this is probably a hexagonal system, and this is probably a tetragonal system, right? And then all the way down to the bottom here, triclinic, you can think of as these 1s, right? So that's what that's what I want you to get out of this, is general sort of correlation between these symbols and the systems that they are associated with.